Two miners, opposite sides of the world, find valid blocks within seconds of each other. Only one block survives in the chain. The winner isn't whoever found it first. It's whoever's block reaches the rest of the network first. Every millisecond of propagation delay tilts Bitcoin toward whoever already has the most hash power. To understand why every millisecond matters, picture a block finding race. Miner A in Tokyo solves a block. Miner B in New York solves a different valid block almost simultaneously. Both blocks fan out across the peer-to-peer network. Each node accepts whichever it sees first and starts mining on top of it. Eventually, one side gets extended with a second block. That chain wins. The losing block becomes a stale orphan, and the miner who found it earns nothing. Whose block wins comes down to propagation speed. If your block reaches more hash power faster, more miners build on top of yours. Slow propagation systematically favors large miners. A miner controlling 30% of hash power is 30% likely to find the next block themselves, instantly extending their own tip with zero delay. A small miner with 1% has to wait for the network. So the bigger you are, the less propagation speed hurts you. Fast block relay is therefore a decentralization issue. Shaving milliseconds off announcement times lets small miners compete fairly against industrial farms. This is why Bitcoin developers obsess over the size of a block announcement. Here's the key insight. Every full node stores unconfirmed transactions in a buffer called the mempool, waiting to be mined. When a new block arrives, its transactions are almost all already sitting in everyone's mempool. Resending them is pure redundancy. Bitcoin Improvement Proposal 152, Compact Block Relay, exploits this. Instead of sending full transactions, the sender ships a tiny identifier for each one, and the receiver reconstructs the block by looking those identifiers up locally. Here's how BIP 152 works. For each transaction in the block, the sender computes a 6-byte short identifier and sends only that. The receiver scans its mempool, matches each short ID to a full transaction, and rebuilds the block. The coinbase transaction, which pays the miner and is unique to this block, is always included in full because no one has it yet. When mempools agree, this hits 97 to 99% bandwidth efficiency. A 1 megabyte block of transaction data shrinks to roughly 10 to 30 kilobytes on the wire. If the receiver is missing a few transactions, it asks for just those. Otherwise, reconstruction is instant. One clarification: compact blocks do not make blocks smaller. The block stored in the chain is exactly the same size. Compact relay only shrinks the wire format between peers that already share mempool state. A brand new node syncing from scratch still downloads every full transaction. This is a relay optimization, not a blockchain optimization. Compact blocks are clever, but Bitcoin Core actually offers two modes for using them. In low bandwidth mode, the default, a peer announces only the 32-byte block hash. Your node decides whether it wants the compact block and requests it. Safe, but one extra round trip. In high bandwidth mode, the peer pushes the compact block immediately after only checking the proof of work in the block header. No full validation first. That sounds reckless until you price it out. Faking a valid proof of work header costs roughly $150,000 in hash power. Nobody burns that to slow down a relay. To keep traffic sane, Bitcoin Core uses high bandwidth mode with only 3 peers. The other connections stay in low bandwidth mode. The naming is misleading. High bandwidth mode still uses dramatically less bandwidth than Bitcoin used before BIP 152 existed. It's just slightly heavier than low bandwidth mode. Compact block relay is the best the public peer-to-peer network can do. To go faster, you have to give something up. Enter private relay networks used by professional miners. First trick, forward error correction, or FEC. Normally, if a packet drops between Alice and Bob, Bob has to request a retransmission. That round trip can triple total delivery time. With FEC, Alice sends extra redundant chunks up front. Bob reconstructs the block from any sufficient subset. Even if some packets vanish, no retransmission needed. Second trick, pre-validation relay. A relay node assumes its neighbor's mempool matches and forwards FEC packets before fully validating the block. Third trick, routing through data centers parked next to transoceanic fiber cables, where latency is bounded by physics, not the open internet. Together, these can cut propagation across continents to a few hundred milliseconds. The catch: every shortcut requires trust. Data center operators can snoop on traffic. Pre-validation relay can be abused to flood the network with garbage. These tricks work only on accountable centralized networks. The flagship example is FIBRE, the fast internet Bitcoin relay engine. Matt Corallo built it in 2016, replacing his earlier Bitcoin relay network from 2015. FIBRE runs over UDP, the connectionless internet protocol, so it skips retransmission overhead. It combines compact blocks, FEC, and pre-validation relay across a global mesh of data center nodes. Miners who need every millisecond plug into it. FIBRE sits alongside the public peer-to-peer network. It does not replace consensus. Bitcoin's design constantly balances speed against trustlessness. Compact block relay is the rare optimization that helps both. FIBRE is faster, but only by accepting centralization trade-offs the base protocol can't. Every byte and every millisecond shapes who gets to mine.